Hello, and thank you for joining me. My name is Laura Stridiron, and I'm a Senior Product Marketing Manager for Aspen Tech, specifically focused on Aspen's Asset Performance Management Suite. Today, I'll be talking to you about an exciting case study in Brazil, where Braskem troubleshot and rectified over $1 million in losses to flare in their depropanizer column using Aspen's ProMV solution. Before we get into the specifics of the case, I'll give you a brief overview of Braskem as well as ProMV. And this will be followed by the background and motivation of Braskem's approach to this issue, the challenges they faced, the methodology of the approach, and of course, the benefits and savings realized from the effort. For those that aren't familiar, Braskem is a Brazilian petrochemical company headquartered in Sao Paulo. The company is the largest petrochemical company in Latin America and has become a major player in the international petrochemical market. Their reach includes over 70 countries and 8,000 team members. ProMV is a powerful multivariable solution available from Aspen Tech. The globally known statistician John McGregor was the original creator of ProMV. During his decades of work in the industrial processes realm, he saw a gap in some of the tools that were available. They all required a deep understanding of data science and statistics to use. And this meant that those most familiar with the processes, a process engineer, for example, couldn't easily overlay that intimate knowledge of the process within the analysis. And this meant a gap in terms of limiting the effectiveness and timeliness of the results, and then therefore increasing the time to value. ProMV was created to not only use existing data, but existing engineers as well. Data scientists are a powerful group to have in-house, but they're not always available. Additionally, they might have a large backlog of other projects they're working on. Solutions like ProMV put the knowledge of the existing process engineers to work with powerful analytics that weren't previously available to them. This power is their ability to find out what's truly critical to the stability and the health of a process. You can't control what you can't observe. And sometimes issues that are creeping into, say, quality, or in Braskem's case, losses to flare, maybe due to things that aren't either associated with the particular issue at hand or associated with the product in question, or possibly not currently monitored or manipulated. With the technology behind ProMV, customers can more quickly identify those factors that are most critical to the end variable that's under consideration and give more focus and insight to the efforts of the plant support staff or, say, APC engineers. And this could be done and be examined across hundreds of process variables. And then ProMV's online capabilities will continually monitor those behavior changes among those variables to alert when an end product, say end product quality, might be at risk. And this could be alerted before a threshold alarm is even triggered for, say, a temperature or pressure. Like many industries, Braskem is evaluating tools to increase the use of digitalization in their process. They're specifically looking for ways to support and validate operations decisions, increase process knowledge, improve troubleshooting, and refine their process monitoring capabilities overall. And this is what led them to select the depropanizer case for investigation. In terms of this facility, it receives different feeds and then it proceeds to separate the C3 in the top of the column and the C4 plus to the bottom. Further downstream is where they're referring to the depropanizer, and this is where they separate the C4 at the top and the C4 and other components at the bottom. The problem was that losses of propane, which is one of the heaviest C3s in the first column, were going from the first column then downstream to the depropanizer. When this leakage happened, it resulted in pressurization issues. The presence of that C3 caused the pressure to increase more precisely. This pressure increase meant the need to vent to flare. The top of the debutanizer column, however, contains some high-value chemicals like butadiene, and that flare meant production losses, which in 2017 was on the order of about $1 million US. Different approaches to investigation were done, and at the point of this case study, they even had plans to change the column reboiler to be able to increase the heat exchange capacity. The column itself already had 2 reboilers, but they weren't intended to be used in continuous operation. One was a spare whenever the other reboiler was being cleaned. So over time, they started trying to test the use of 1 reboiler versus 2, but this meant they didn't have a spare. So the new capital project was looking to adding to that reboiler capacity so that they would be able to run 2 if needed. If a solution could be realized with ProMV, it would mean not only saving in that loss to flare, but avoiding a capital project. Based on the challenges that I just mentioned, Braskem set out to ID the root causes of the losses, as well as know what the key components of the process, these key variables of the process were that impacted the losses, with that ultimate goal of improving process performance and, frankly, evaluating the usability of ProMV. There were some challenges and some specific questions that Braskem was looking to tackle in terms of what data they used and how they went about the analysis. The first was some of the instruments were calibrated over time, which would impact the data sets, of course. So for this reason, they needed to delineate what data was before the calibration and after the calibration, and part not just for data cleanliness, but also they wanted to see, did the calibration have an impact on the loss of flare that they hadn't been able to ascertain before. And then based on the operational tests of running 1 reboiler versus 2, they wanted to further dive into that as well and look and understand the results of operating those 2 different ways. Obviously, the preference was to be able to operate 1 reboiler and not 2, both for just having the spare and cleaning, but also to keep favorable maintenance costs. Most importantly, they wanted to determine how did they need to operate just to minimize those C3 losses. They needed to include all the data that they could capture during times of high C3 loss and during times of low C3 loss, as well as any variables that could influence the results, and more specifically, anything that they could potentially manipulate or use as control within their process. From a data collection standpoint, this equated to about 22 months worth of data with average hourly measurements. This meant over 15,000 operations centering on observations, not operations, centering on that single output of C3 losses. And as I mentioned in the previous slides, this was broken out by times before and after calibration, as well as the operation of 1 versus 2 reboilers. Then, in order to prune the data, they also needed to look for were there times that they needed to eliminate because they considered it abnormal operation. So, for example, a truck strike in Brazil, or times when there were low operational feeds being processed. ProMV has tools within it to more easily help you identify and remove outliers from the analysis. The comparison of the models using 1 and 2 reboilers was done to determine what were the key contributors and the variables that related to those high and low C3 losses, as well as the times before and after calibration. They then did what they call a group analysis. They got a bunch of engineers into a room and they looked at what were those key contributors that ProMV was indicating and discussed how best to troubleshoot it. And then lastly was the implementation stage and realizing the benefits. With the first question in the analysis being how to determine the impact of the calibration activities, Braskem needed to further disperse the information, not have it so clustered. Within ProMV are tools and capabilities that take large amounts of data and distill them into more easily understood representations. And one of these is group-wise mean centering and scaling. The figure on the left shows that the data without the group-wise function enabled. The black points represent operation before calibration, the blue is after calibration, and the orange is during a period of transition. On the right-hand side, you see the same data, but with the group-wise function enabled. And this data is much more dispersed and less clustered and provides a lot more context to the information. The next challenge was determining the impact of using 2 reboilers versus 1. And for this, they created a PLS model in ProMV. On the right, you see an operations map of latent variables and colored by the amount of C3 losses. So it's very easy to see where the high regions are and where the low regions are. And on the left, the black marks indicate the use of one reboiler, and the orange marks indicate the use of two. So if they compared, when they compared the right and the left graph, they could easily see that the number of reboilers in operation was definitely a contributor to C3 losses. But there were regions where there were low C3 losses and only one reboiler, which is where they wanted to get. So it confirmed that they had the opportunity to achieve what they were looking for, but now they needed to dive into how to do that. ProMV then allowed Braskem to center in on the results that provided that combination of one reboiler and low C3 losses. You can see from the graphic on the left the points that are highlighted by red boxes and blue circles. These operating regions were selected by the user as they were the states they wanted to investigate and see what were the biggest contributors to those high and low C3 losses. From there, ProMV created a contribution plot that showed those variables that I just mentioned, providing the highest contribution to the selected operating points. Looking more closely at that contribution plot, was specifically what the group looked at in that group analysis step of the methodology that I mentioned earlier. It was obvious what variables were higher weight based on the size of the bars on the chart. But in some cases, these were the first time that they were seeing them. In some cases, they were known, like flow rate. In other cases, they were things that couldn't be changed, like feed stream. But specifically on column temperature 12, this was something they hadn't seen before. It wasn't the control temperature for the column and wasn't anything on anyone's radar screen at that point. Other plots were created to confirm that influence of these variables and specifically drill into the temperature of tray 12. The graph on the right is the raw data for tray 12 temperature. The red squares show the lowest C3 losses, and it's easy to see that these correspond to the highest tray 12 temperatures. Similarly, the blue marks correspond to the highest C3 losses and the lowest tray 12 temperatures. When analyzing this, different possibilities for how to address the issue began to appear because they knew this contributing factor. And Braskem realized that it was necessary to change the control temperature from a point on the column where the area was above the feed streams to tray 12, which was located below the lower feed streams. To reiterate, at the beginning of the analysis, the control temperature of the column was not on their radar as a contributing factor and was only highlighted with ProMV. So in summary, based on this analysis from ProMV, Braskem determined that using the tray temperature indication above the feed stream was not the appropriate variable for controlling reboiler steam flow, and that the tray 12 temperature below the feed stream should be used. That led to another question. What temperature set point should be used to minimize the C3 losses? And this is where ProMV Optimizer comes in. Focusing on the data set using one reboiler, the process was optimized to not only minimize C3 losses, but maximize the feed stream, all while ProMV took into account the constraints that were considered feasible operation. And ProMV does this just by looking at the data history. The result was tray 12 temperature needed to be above 56 degrees Celsius. Braskem was very pleased with the speed of discovery of the solution, especially when compared to the proposed alternative of a capital project. The findings were easily implemented and the benefits were realized quickly. The graph on the screen shows tray 12 temperature and C3 losses before the analysis, during the transition period when adjustments were being done manually, and following the change in the control temperature. It's easy to see that not only are there reduction in losses, but the stability of the variables overall. The stability is what has allowed Braskem to save over $1 million in losses of high value production to flare using ProMV. Having proven the value of ProMV with the depropanizer, Braskem is now also using ProMV to study and monitor furnaces in order to minimize energy consumption. According to Braskem, ProMV is a user-friendly solution for multivariable analysis, but they're sure to note that the data alone won't solve the problem. And as I mentioned earlier, being able to bring in that human knowledge to interpret the data is necessary to complement that analysis. And that was the specific goal in creating ProMV from the very beginning. Thank you for your time to hear about this exciting case study. I do realize I went through some details fairly quickly, and there are likely a lot of questions. Earlier in 2019, Braskem delivered a webinar on this specific case, complete with an extensive Q&A. To access the playback, you can head over to the AspenTech website and type Braskem in the search bar. With that, I will say thank you, and thank you to the attendees, and thank you to BlueESP for the opportunity to present. Please enjoy the conference.